Okay, Bismillahirrahmanirrahim and Assalamualaikum to Madam. Okay, today I will present to you about our assignment, group assignment. Okay, so this is my team. My name is Adam Mokrish bin Ahmad Azizi. My metric number is B0821100158 and this is my team also, Muhammad Rushaidi and Muhammad Daniel. So now I will talk to you about the introduction. Okay, PowerWorld is a robust software to design for the analysis and simulation of power system, offering engineers and operators a comprehensive platform to model an optimized electrical network. This step-by-step journey provides instruction for creating a new power system case for scratch within PowerWorld, offering insight into fundamental actions such as bus and generator insertion, transmission line configuration, load and switch shunt placement, and visualization settings. By following this instruction, users can understand the process of building a basic power system model, setting key parameters and utilizing visualization features to observe dynamic behaviors such as power flows. This tutorial aims to familiarize users with the essential functionalities of PowerWorld, fostering a foundational understanding of how to navigate the software and leverage its capabilities for effective power system analysis and simulation. In this project, students are given a task to create a power system with specific features. The focus is on visualizing real and reactive power supply to the load using green and blue arrows, respectively. The size and speed of the green arrow should show the real power, while the blue arrow represents the reactive power. To make the system more efficient, a capacitor is added to compensate for the load, and its output, Q cap, can be adjusted in increments of 0.5 MVAR within the range of 0 to 10 MVAR. The next step involves plotting real and reactive power line losses against varying Q cap value within this range. By closely examining the graph, student aims to find the Q cap value that minimize both real and reactive power line losses, optimizing the power distribution system's efficiency. Identifying the optional Q cap value allows students to determine the corresponding power factor PF at that point, enabling a comprehensive analysis of the system performance under different load conditions and facilitating the identification of the most efficient configuration with minimized losses in both real and reactive power. So that's all for me. We move to the next, to the Daniel. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Daniel bin Anang Syafizanwar, and I will present how we get the data from the simulation. And this is my circuit that I construct. Follow the instruction. First, this one is a generator, is this one, and the bus one, this is a switch shunt, and this is a load, and the bus number 2. First, from the data that we get, how do we construct, and we get this first run the circuit, and then we set the Q cap. So Q cap at the 0. Q cap will automatically increase when we set 0.4 and 0.8. So we set at 0, and then we get a P losses and Q losses when we double click at this line, and we get the P losses and Q losses. So also that we can get the generator. So we click at the generator, and we get the P generator and the Q generator. So Also that we can find the power factor from the calculation. So we get the P generator and the Q generator, and we put at the calculation. We find the theta equal to tangent inverse Q over P, and we get the theta. After that we use the power factor formula. Power factor equal to cos theta, and we get the power factor. After that I will explain about the graph Q cap with SP losses and Q losses. At the 0 to 9.7 Q cap, both P losses and Q losses show variation. Notably, the average power factor across all Q cap value in 0.9466, indicating generally high electrical efficiency. From the Q cap value from 3.6 and 5.7, P losses decrease from 0.701 to 0.360, and the Q losses decrease from 0.710 to 0.721. In practically term, Q cap value between 3.6 and 5.6 could lead to minimize the power losses and higher overall power system efficiency, as indicated by the evaluate power factor. For the graph 2, as Q cap representing reactive power increase from 0 to 9.7, there is a consistent decline in power factor, initially starting on 0.87 with no reactive power. Q cap at 0, the power factor gradually improve, reaching 1 when the Q cap is 3.6. However, as Q cap continues to rise, the power factor start decreasing. This suggests Q cap at a 3.6 to 6.2, where the system achieve a balance between the real and the reactive power, resulting in a higher overall efficiency. Beyond this range, the system experience a decline in power factor, indicating a less efficient use of electrical power. That's all. Thank you.
My name is Muhammad Azim. Okay, for discussion, the provide data present a power system with details like power generation, losses, and phase angle. Looking at the number, we see change in power factor and losses as the system evolve. Power factor, a measure of electrical efficiency, fluctuate between 0.87 and 1, with a consistent decrease. The phase angle shift from positive to negative value, indicating a change in the system reactive power. Power losses far affecting both real and reactive power components. Additionally, as the generation decrease, the losses and phase angle also change. This data offer insight into how the power system respond to different conditions, helping engineers and operator optimize its performance. For the conclusion, the analysis of the power system data reveal dynamic change in power generation, losses, and phase angle. The influencing power factors suggest variation in electrical efficiency, while the shifting phase angle indicate alteration in reactive power. Notably, as power generation decrease, there is a discernible impact on losses and the phase angle. This finding underscore the system adaptably the responsively to different operate condition. Engineer and operator can utilize this information to fine tune, and system will improve in efficiency and stability. The data insight contribute to the data to be better understanding of how the power system behave under very constraints, guiding decision for optimal performance and reliability in electrical network.